This video is going to be part of Activity 1, where we design and build and test half-wave rectifier and the full-wave rectifier with the AC power supply. When I do the initial calculations for this, I'm going to be using the voltage peak of the power supply rather than the Vrms. The minimum that you need to know about a rectifier is that it is the electrical equivalent of the mathematical function absolute. It's really as simple as that. In an ideal world, this black box would give you, regardless of what is on the input, a positive on one wire and a negative on the other wire with a magnitude that matched the input. So if you gave it plus 16, you would get out 16. If you gave it minus 16, you would get out positive 16. So furthermore, what that means is that if we were to feed it a positive voltage that didn't change over time, and the voltage happened to be 16 volts, then the output would be exactly the same, an output of 16 volts that didn't change over time. On the other hand, if we gave it minus 16 volts, at the input, we would get positive 16 volts at the output, also not changing over time. The only thing that makes the output change over time is the magnitude of the input changing over time. So this is where we come into the AC waveform, or not necessarily a sinusoidal waveform. It could be a square wave, it could be anything. And if we were to give it a waveform that did change over time, like a square wave, then the output would also change over time, but it would be always positive. I'm only drawing these lines to show where the voltage changes at the input. And realistically, there will be dips in voltage briefly when it changes, because it has to pass through zero and that takes time. But ideally, this is an extremely short duration drop to 0 volts, and then immediately comes back up to the positive 16. With respect to our rectifier circuit, since we're feeding it a changing input, the output is also going to change over time. If we have a constant input voltage and a constant output voltage, the peak voltage of 16 volts is also going to be the average voltage. Regardless of whether the input is positive 16 or negative 16, the output is going to be positive 16 at all times. So a number that doesn't change, that number's average is the same number. In the case of the square wave, if you were to take the average value of a square wave that had a 50% duty cycle, meaning that it's half plus 16 and half minus 16 over time, you would find that the average voltage is 0. Because the 16 is almost continuously positive 16, then the average is 16. And the peak is 16. They're the same. You have a gradually changing value over time. You do have a peak voltage that is literally the highest voltage, which is a peak of 16 volts. But if you were to integrate all of those voltages over time, you would find that the average voltage is actually the peak voltage divided by the square root of 2. Why this is important is because, first, some components are very sensitive to voltage, and if you give them too high a voltage, they can be damaged. So if you design for the average voltage, then 120 times per second, you are stressing the component with more than the average voltage. So the voltage peak equals Vrms times square root of 2, which is 1.414. Now, what this means is that if you design your LED circuit based on the assumption that you want 20 milliamps to be the maximum current, but you use Vrms in your calculations, when the circuit is running, there will be a peak current through the LED that is 41% higher than the 20 milliamps that you wanted it to be. And that may damage the LED, or at the very minimum will shorten its lifespan.